So far, we've talked about four methods to compute derivatives: symbolic differentiation, finite differencing, complex step, and algorithmic differentiation. Today, we'll talk about a fifth method that's primarily useful for implicit functions. You'll recall that we talked about implicit functions at the beginning of when we were discussing derivatives and also in the numerical methods section. But here's that simple example we looked at before with a scalar where um, for some input x, we cannot explicitly solve this for f. So it's an implicit equation. We need some sort of iteration, um, some root finding method in general to solve these. So we're taking, this is a diagram we looked at before. We could, for example, think of our functions as black boxes, only concerned with inputs and outputs. And finite differencing is well suited to that type of a model. If we look at individual argument or operations, algorithmic differentiation is very effective. Of course, symbolic differentiation could potentially be done as well, but as we saw, that doesn't generally scale. Today, we're kind of looking at this level where we're not looking at individual operations, but rather blocks of solvers. So often within some larger code, we may have sets of equations that we need to converge, that we need to solve. Generally, these implicit functions that we need to solve. And we say equal to zero because that's general. We can always move everything to one side of the equation. This is just to suggest that there's some set of residuals. We call these residuals because we're trying to drive them to zero. Okay, so this was, again, that simple function that we did. And while not a good method, right, we showed before we could do a fixed point iteration. So we could do something like for I equals 1 to n, just keep updating f using some initial guess for f, right? Let's just say f is, let's just start with x, for example. And then we could wrap this whole thing in a function. We could say, okay, this is a function, and let's call it, this was actually motivated by Kepler equations. Let's say this is an orbit function. You give it x, and we return f, and that's it. So there's a function. And we could finite difference this, right? It doesn't care that there's some iterative thing happening in there. We could use complex step. We could use algorithmic differentiation. Any of these methods we could use. And as long as this n is large and we have a reasonable starting point and it's well behaved, this should work. But as we've discussed, fixed point iteration is not, it's prone to convergence issues and is not particularly efficient. But, this is just to illustrate this example here. So while we could do the things that we're suggesting, right, like roll AD through the solver or finite difference around the solver, there's actually a better way, or generally a better way. There's an alternative way that's often better. And that's what we're going to discuss today. So let's start very basic, just to kind of think about these problems to get warmed up. Let's say what we've got here, and maybe this is the opposite of the order we should think of these occurring, but we have some output that we care about, f, right? That's what we're trying to compute, and x is an input. Okay, so x is an input to our function, f is what comes out. And x also depends on this variable u, and u is related to x as described here. And at the end of the day, what I care about is df dx. Now, in this case, this is really simple because we can actually explicitly solve for u, right? On this bottom equation, I can say, okay, let's move the 2 over, multiply by x, u is minus 2x. I plug that in, I get f equals minus 2x cubed, and of course now taking the derivative is easy. Okay, but what if I just changed one thing? I have that same function, but now I change this term here. I can no longer do that trick, right? So still, x is the input I want, f is what comes out. U is now an implicit function of x, right? Because I specify some x, u is not an independent variable. I can't choose u. It's determined by satisfying this equation. And I can't explicitly solve that, so I need to use some root finding approach to determine that. But once I do, I can plug those in and I can get f. So by way of nomenclature, we call this variable u, we call that a state variable. Okay, and we distinguish it because, again, it's not something that I have an independent choice of. It's not an input or an output. It's something that's determined by x. So u, the state variable, is actually a function of x, right? It's determined by x. by solving this residual. Okay, so let's try to figure out how we might take derivatives, because remember, what we want is df dx. So I encourage you to pause now, take a few minutes and try to see if you could figure out how to compute df dx symbolically here. Okay, so let's just think about how we might do this. So let's just attack this directly. If I want df dx, let's just go after df dx and then try the chain rule. So I could say df dx, now u depends on x, as we just said, so I need to use the chain rule here. So this is a product rule. So I could do, for example, u times 2x plus du dx times x squared. Okay, so that's good, but I have the problem now that I have du dx, and I don't know what that is. So let's jump to our second equation here. Maybe let's differentiate this equation. So let's just try that. Let's take the derivative with respect to x. So now I've got this quotient rule. It's going to be something like this: x times du dx minus u, derivative of x is 1, all over x squared, minus sine u times du dx, assuming I did that right, which I may not have. And, I'm taking the derivative of x with respect to both sides, so it's still just equal to 0. Okay, and, I may have made a mistake there, but I think that was okay. So perhaps what we could do here, you could see I could conceivably solve for du dx and plug that in, and I'd have an expression in terms of x and u, and u is something I can compute, right? It's a function of x. So this may work, but this is a very specific case. So it's not clear this is going to work in general. So let's try and back up and do this more generally. Just trying to motivate this here. Here's a diagram of maybe this more general problem, right? Again, x is in, f is out. Here's our state variable, and we've written explicitly, right, that we have some set of residuals we're trying to converge, right? This is going to be in general a bunch of equations, a bunch of unknowns, and x is an input, but u is not something I'm free to choose. That's those state variables that I'm converging to, and so that comes out. And so u depends on x, right? And f, this output, is in general a function of both x and u, right? It may depend on both of these variables. And again, we're writing explicitly that u depends on x here, right? And after I compute f, I get the outputs that I want. So these are some downstream things that may occur after this residual, potentially. Okay, well, let's again try to do this generally. Let's write those out again. So what I have is I have some function that I care about, f, and it depends on x and u, but u depends on x, right, through that residual relationship. I also have a residual. It's in general a function of x and u, right? And the residual is just a function. I can evaluate it anywhere. I can evaluate it and it can give me any number, but I know it's solved once that residual goes to 0. So that's going to give me the right value of u. But to be clear, the residual is just a function. So if we went back to this case, this whole thing is just a residual. It doesn't necessarily give me 0, or I can plug in a u and an x, but by solving this equation, finding where it does equal 0, that's how this u pops out, right? And so that's what I'm trying to do here. So that's the setup. Let's do something similar to what we did last time. Let's go after what we want, which is df dx. Okay, so let's take the derivative of f with respect to x, and now f depends on multiple things, x and u. So we're going to have to take partial derivatives, and we're going to have to use the chain rule here because u also depends on x. So this is going to give me the partial of f with respect to x plus, now my other variable, the partial of f with respect to u, times, I got to now use the chain rule, du dx. I need to know how u varies with x now by the chain rule. Okay, it may be worth, if this is, if you're a bit rusty in this, reviewing how total derivatives and partial derivatives differ in the appendix of the book. But briefly speaking, this total derivative, that's much harder. That's asking, if I change x, how does f changes under this condition, right, that this is solved? The partial of f with respect to x is a much easier thing. That just says assume everything else is constant. So u is constant. So in other words, the residuals are not necessarily still maintained as I change x. I'm just saying x is constant. I just want to know the sensitivity of this function with respect to x, ignoring everything else. Right? Okay. So that's good. I've got partial derivatives that are not too hard, but then I've got this total derivative, which is going to be difficult because again, that's requires iterating to solve that residual. So let's do the same kind of thing we did last time, or in the simple example, and let's take derivatives of a residual also. So let's take the derivatives of the residual, and it's going to be basically the same, right? I've got the partial of r with respect to x. Since r depends on both things, I've got to take these partial derivatives with respect to u, and then via the chain rule, since u varies with x, and I'm taking the derivatives of both sides, and since my residual must stay 0 for this total derivative to for the equations to be satisfied, then this should also be 0, right? I just took the derivative of both sides with respect to x. Okay, so again, I've got some partials which aren't too hard, but I noticed that this total derivative is the same in both. So I can potentially now, since I have an equality here, solve for this one and plug it in. So that's exactly what I'm going to do. Let's take this term and move it over. So I would get the partial of r with respect to u times du dx equals minus the partial of r with respect to x. Okay, and I want to solve for du dx. I have to be a little careful here because we're trying to do a general case, and so we're not dealing with scalars anymore, right? X is a vector, u is a vector, r is a vector, f is a vector. So this is a matrix, right? It's a Jacobian matrix. And this particular one is square, but most of these are not necessarily square. But this I know is square because I have to have the same number of residuals as states, right? So I have a set of equations I can solve. But okay, so I'm going to multiply by both sides by this inverse. So if I multiply by the inverse of that, this will become the identity and go away. So I'll have the inverse over here. So I get du dx equals minus, I'm multiplying by that inverse, partial r partial u inverse times partial r partial x. Okay. Now that I've done that, I can take this term here, right, du dx, and plug it in, and that'll give me my final expression. So I've got df dx, the derivative I want, is equal to these terms here, right? Partial f, partial x, plus partial f, partial u, and actually it's going to be a minus now because I'm going to bring that blue part over, partial r, partial u, inverse, partial r, partial x. Okay, so it seems like, we did a bit of math gymnastics there, but we've got actually a nice expression here. The nice thing about it is that this total derivative that I want only depends on partial derivatives. And partial derivatives are much, much easier to come by. They don't require this iteration, right? Seeing how the function changes under this solve. So we can get them pretty quickly, and we'll see that. So this is, again, it's kind of like the 1D case that we just looked at. Similar idea, but we've generalized it and we've come up with this formula. All right, so let's look at it before we talk about how to solve this, more generally. Let's just go back to those simple 1D problems that we had, just to kind of see what that would look like. So let's first do the motivating problem we had, which was f is, and actually I'm going to write it. Oh, that's fine. I'll write it like that. U times x squared. And then we had, what was it? U over x plus cosine u. U over x plus cosine u equals 0. Okay. And since this is already in the form of a residual, I've already moved everything over. This is r, right? That is my residual, that function here. This function is my residual function, and this is my output f function that I'm interested in. Okay, so what I want is df dx, right? I want to know how this output changes with respect to x, because again, remember, this is just some function here with x coming in and f coming out and u being a state that's solved internally. Okay, so let's write down the formula we had. Df dx is partial f partial x minus partial f partial u times partial r partial u inverse times partial r partial x. I think that's right. Yep, yeah, that's good. Okay, so let's just work out those terms. In this case, partial f partial x. So remember, the partial derivative, this is the partial of f with respect to x, means that everything else is constant. U here is a constant, okay? I don't have to go and figure out how u changes with x and solve this. Just use a constant, so this is straightforward. Just a constant, so I'm just taking the derivative with respect to x, so I get u times 2x. Similarly, the partial of f with respect to u, x is now a constant, right, because it's a partial derivative. So that x squared is just a constant that comes out, and the partial of u with respect to u is just 1. So that's it. And now I need the partial of r with respect to x. And again, the residual is this function here. So if it's with respect to x, that means u is a constant. So I just pull out that u here. That becomes minus u over x squared. And then cosine u is a constant, so that the derivative of that is gone. Okay. And then finally, partial r partial u. That means x is a constant. So I've got 1 over x. Then the second part, the derivative of the cosine, is going to be minus sine u. All right, so that's it. I'm not going to do the last step. You just plug those into the respective spots where they go. And in this case, because the scalar inverting just means divide, right? It's just going to go into the denominator. But that's straightforward, and it just depends on x and u, right? I have to solve this anyway. So when I solve this, I do get u, so I know what u is. It's a function of x, right? So this gives my derivative nicely here. All right, now let's look at an alternate case here. Let's do the problem that we were doing, actually, just for fun. That simpler problem, because it actually has a little bit different feature. F of sine of x plus f. Okay, and I want df dx. So I'm going to erase this stuff so we can do it again. I would encourage you to try it first, and then come back or unpause, and I'll do it for you. Okay, so if you tried that, we have to. This is going to be easier if we rewrite this in the form that we're used to here. So it may be somewhat confusing because I've used f here, but this is our residual equation. So f is actually our state. So in this case, f is u, right? So this is actually u, and we're going to write it in residual form. So I'm going to move everything over, and it doesn't matter which way I move it over, right? It's going to be the same either way. And so this is our residual equation, R. Okay, and that's it. There's nothing downstream of this. So my f is u. And so that's all I've got here. So this is fairly straightforward. So df dx, that's the partial of f with respect to x, but f is just u, so it doesn't depend on x at all, so that's 0. Partial of f with respect to u is just 1. The partial of r with respect to x, so now I got to go look at this term, partial of r with respect to x, so u's are constant, so that's going to be, a minus cosine of x plus u, I believe. And now the partial with respect to u is going to give me 1 minus cosine of x plus u. Okay. So assuming I did that right, I get that df dx for this expression here is going to be, I'm plugging everything into this thing right here, a minus, because partial f partial x is 0, partial f partial u is 1. The partial r partial x, this term here, has a minus sign in it, so it actually cancels that minus sign. I get cosine of x plus u divided by 1 minus the cosine of x plus u, because that's an inverse, right? But again, this was a scalar, so it just became a division. All right, just for fun, let's go try that. Let's see what happens, see if that works. Let's share a different screen here. All right. So I'm just going to define a function really quick here on the command line, just the one that we talked to, and we'll just call it f. Well, let's call it orbit, because that's what we called it. And we'll say u equals x, and for I equals 1, 2, let's just do some really big number so we can be sure that we're going to get an exact number here, because we're going to compare. We want to see if this is exact. U, let's see, equals, I'm trying to remember what the problem was, u plus x, is that right? And then let's return u. That's it. So let's say x is 0.1, for example, and we could evaluate our function. Oops, I didn't mean to do u. Evaluated x, and let's say that's what u is. Great. So we just use some solver, and just to, as comparison, we're going to use a forward mode algorithmic differentiation, and we're going to use algorithmic differentiation in this loop. So it's going to do the AD through the loop there. So let's do that derivative of my orbit function at x, and that's the derivative, right? So I did forward algorithmic differentiation. All right, so I just derived an analytic solution to that derivative, even though it's implicit, and let's just check it. So let's think I got cosine of x plus u divided by, assuming I did this right, 1 minus the cosine of x plus u. And looks like we did it right? So we get an exact match all the way down, right? So great, that's cool. So let's go back. So then we might wonder, well, I mean, why do we want this? Well, for something simple like that, it's maybe less obvious because, I mean, AD will work fine. You can see, though, that it is going to take more computation because we're going to have to run that AD through the loop. Let's dive a little more. This is going to be especially important as we have, I mean, it's very popular with like PDE, partial differential equation type problems where we've got a set of functions that taking an analytic derivative is not complicated because we have these set of governing equations, but but they're very expensive, right? And so we really want to be able to do these derivatives efficiently as possible. And there are actually two ways to solve it. So let's go back. Here's this governing equation. And let's go back and think about the general case, because here we did this little 1D thing. Let's think more about the general case. And there are two ways to solve this. This first method is called the direct approach. So if I was writing this out again, let me just write the whole big equation again. It's df dx equals partial f partial x minus partial f partial u times partial r partial u inverse times partial r partial x. Okay, all right, so I just wrote it all out. Okay, so the reason why there's two ways to solve is we actually don't do this, right? We don't invert a matrix. That's a very costly operation. We're going to solve linear systems. But there are two different ways that we could solve it that are going to lead to different behaviors. So just for convenience, let's define this term here. We're going to call that phi. So we're going to say phi is that term, right? Partial r, partial u, inverse times partial r, partial x. Okay, so in other words, I'm going to now move this over. So I'm going to multiply by partial u on both sides, partial r, partial u. Right, so if I multiply on the left by partial r, partial u, then on this side, those will cancel out and give me the identity, and I get partial r, partial x. So this looks like an equation ax equals b, but keep in mind here, right, this is a matrix. This is a square matrix. This is generally a non-square matrix because the number of inputs is unrelated to the number of states or residuals, and the number of residuals and states are going to be equal. But in any case, where I have a matrix and a matrix. So the way I'm going to solve this is I'm going to solve this for one column of this matrix at a time. So right, this is a big matrix potentially. If I take one column of it at a time and I just look at that one column, then this is a linear system of equations, right? This is going to be a x equals b. So I can solve for phi one column at a time, right, from this linear system. And once I solve phi, right, well, let me write that explicitly. Once I solve phi, I plug it into here. And so I would get df dx equals partial f partial x minus partial f partial u times phi, where phi is this vector. So this is a matrix minus this matrix vector product. And then, so look how this is going to go. I have the most expensive thing here, right? This is cheap. Matrix vector operations are cheap. Taking the partial derivatives is fast. The part that's expensive is solving this linear system. And notice I have to do it once for every column of this Jacobian here. And so that means this is the partial r with respect to x. So this is going to be once for each x. So one solve per x. Okay, so I solve this for a given x value, one column here. That gives me a phi. Once I have that phi, and then I can multiply it across here and get all these derivatives with respect to 1x. But notice also, well, I have to do this one solve per x, that this expensive part, the solving the linear system, and this is expensive. I say expensive, right? You're probably used to linear systems not being very expensive, but we're thinking these large PDEs, these things, can become really, really big, thousands or millions of variables here. So notice here that this equation has no dependence on f, right? I have to do it once for each x, but it doesn't matter how many f's there are. It doesn't change the cost of this expensive part at all. So once I solve this for 1x, here's where the f's show up, but that's just matrix vector multiplication. So I can add more f's here, and it costs me very little. Compared to this expensive part, it's basically free. So this direct method, we also call it the forward mode, which you might have guessed, thinking back to AD, this is just the same kind of principle, that this scales with the number of inputs, but is essentially independent of the number of outputs. So we call this the forward mode or the direct method. And again, as you can tell just like AD, this way to solve it is going to be advantageous if we only have few inputs and many outputs, then this direct approach is going to be advantageous. And as you might guess, we have adjoint, which is also called the reverse mode. Adjoint's a bit more common, but we also call it reverse, just like the forward and reverse of AD. Okay, so let's again write our big equation. Partial f, partial x minus partial f, partial u times partial r, partial u inverse times partial r, partial x. Okay, so instead of solving this part here, we're going to solve this part here. We're going to call this thing here psi transpose. So we're going to say psi transpose. It's a row vector. That's why we put a transpose, because it's being multiplied on the left side of this matrix. So psi transpose is partial f, partial u. I'm just writing it down to be explicit here. Partial r, partial u inverse. That's just a definition. We didn't do any math. We're just calling it that name for convenience. Now, if I multiply, if I take the transpose of this whole up thing and then I multiply on the left by partial r, partial u, I'm going to do that whole thing in one step here. I'm going to get partial r, partial u transpose times psi. I'm just doing that because I want to write it in that kind of ax plus b form. Then I get partial f, partial u. Okay, so again, this looks like ax plus b, right? There's a matrix, but this is still a matrix. So again, what we're going to do, since we took the transpose here, this is still going to be fine. We're going to solve it again for one column at a time. Actually, we're solving for psi transpose. So actually, we do it. Whoops, yeah, that's what I messed up. There's a transpose here. That's why I was confused. Because yeah, first I took the transpose of this whole thing, and then I multiplied by dr du transpose to bring it over. So anyway, this is what I get. So I am doing this for one column of this at a time, and because this is a transpose here, that corresponds to 1f, right? So I do this 1f at a time, right? So one output at a time. So same kind of idea. This is the expensive part. I've got this ax equals b for this one column, or in other words, one row of partial f partial u, or one column of partial F, partial U transpose, whichever way you like to think of it. It corresponds to one F either way, right? That's just corresponding to one F value. That's the expensive part. But like before, notice this linear system solve has no dependence on X, okay? No X dependence here, at least in the solve, in the linear solve part. So that's almost free. And then so once I do that, I get psi, right? I get this vector for each column, and then I plug that back in up here. So just again, to be explicit and write that out, we get df dx is partial f partial x minus psi transpose times partial r partial x. Okay, so this is where x shows up. So again, for each output, I grab this column, I solve for psi, and then I multiply by all the x's. So like the reverse mode, we have to do this operation, the expensive part, for every output. But adding additional inputs has very little cost. This matrix vector multiplication is very efficient. So it's essentially free, essentially independent. So just to recap these two, direct and adjoint, again, you could call them forward and reverse. The partial derivatives, we compute the same partial derivatives either way. Matrix multiplications, they're the same number of operations either way. The main difference is the linear solve. In the direct one, and that's the expensive part, we do it nx times. In the adjoint or reverse one, we do it nf times. So again, it's a trade-off between number of inputs and number of outputs. But this leads to some really powerful ideas. So for example, the adjoint has been very popular in aerodynamic shape optimization because it scales with the number of outputs. So if I don't have many outputs, I can add inputs basically for free, meaning I can add lots of design variables. So I can have these very complicated shapes where I just have lots of design variables so I can change really, really detailed things. And as long as I keep my outputs small, which we can do like by aggregating constraints, as we briefly talked about last time, I can get derivatives for very low cost. All my derivatives I care about. I'm going to show a quick video of that. But before I do that, I should also point out that this, so here's this equation that we want, right? But this is not generally, or not necessarily the final thing per se. And even if it is, we still have to get these partial derivatives. And so how do we get those partial derivatives? Well, we use all the techniques that we talked about, right? So ideally, often we do something like AD. Sometimes they're simple, maybe if it's a PDU, we can get them symbolically. If we had to, but we really wouldn't want to, but we might have to do finite differencing or complex step. Complex step wouldn't be so bad, and that's used. But all the methods we've talked about could be used to compute these partials, and then we can assemble them to get our total derivatives. And again, the main usage for this is these cases where we have these implicit functions. And it's an efficient way to deal with taking derivatives around these solvers. Although, like I said, it's not the only way. We don't have to do that. We could find a difference around them or run AD all the way through the solvers. It just tends to get expensive, especially with the use cases I was talking about where, like I said, where this can't come into play really heavily is with these large PDEs. So for example, finite element analysis or computational fluid dynamics. You have expensive simulations. And if you were to do like a finite differencing or a forward mode AD or something, it'd be very expensive, right? Because you have lots of inputs. You want to have lots of inputs. You got rich three-dimensional shapes. But using these adjoint, we can get all these derivatives and still retain tons of shape variables. Okay, so here's a really simple example, or not simple per se, but just a 2D example. This is from my co-author. This is from Professor Martin's research group. And so let me just explain this first. So what they're doing, this is a 2D CFD, computational fluid dynamics simulation. What we're seeing is they're going to optimize an airfoil in transonic flow here, minimizing drag. Those details aren't important, but to show the robustness of this with these exact derivatives, they're starting from a very bad shape, or they're starting from a circle. And so not starting from something that looks like an airfoil and tweaking it, starting from a circle, but they have lots of variables, so you have a very rich shape. And then we can watch as the optimization progresses. And it's trying to find an optimal shape to minimize that drag with constraints on lift and pitching moment. And there it is. Okay, and that was pretty quick, so let's just do it one more time. And you can see how having those exact derivatives makes this very robust. And it's also due to actually the robustness of this flow solver that they've developed. But a big part of that is developing these derivatives. All right. Okay, so that's it this time. Like I said, this is a powerful idea. The math, it's easy to get kind of lost in the math. For me, I had to look at this and see it probably 3 times before it started to make sense, this idea of an adjoint. But it's a very powerful idea. And in general, the principle we're looking at here is primarily for these implicit equations, that there's an efficient way by knowing the fact that we're trying to converge these things to this zero residual. We can take advantage of that and get very accurate derivatives and still use the techniques that we've been learning to compute those partials, but assemble them to get total derivatives more efficiently. Okay, so we're going to have one more short topic. We'll look a little bit about sparse derivatives next, but it's a bit more of an advanced topic, so we'll only touch on it briefly, and then we'll wrap up this discussion on derivatives.